but I don't think it's necessary that you know how to do those math as much as you have to know how to do molarity. So if you have questions on that math from last class, let me know. This should hopefully be a reminder from Chem 1. For the most part, as you increase the temperature, you increase the ability to dissolve a solid. There is no mathematical expression, however, to detail at 70 degrees Celsius, this is how much sodium nitrate can be dissolved. At 80 degrees, how much potassium iodide can't be. This is something that has to be done experimentally. And we actually did this experimentally in Chem 1. Again, Chem 1 curriculum at times does a real nice job of covering in the holes that we have in AP Chem. It does stuff to prevent me from having to do more work with you guys. Unless you guys think we have more time in our schedule that we can cover more topics. We don't move that fast in this class, right? We can. So remember this third bullet point, that's what we did. Actually, we did this in Chem 1 with potassium nitrate, where we'd heat up a certain amount of solid in water until it dissolved. And then we cooled it down. And at some point, it started to look like a snow globe. It precipitated out. It crystallized. We then recorded the temperature at which that happened, and we can make our own little solubility curve. Last note on this first page. Right before break, I gave you a packet on what was called fractional distillation. I even showed you the distillation glassware that you would use, and in particular, I used it a lot in AP chemistry. In organic chemistry in college. Fractional distillation was separating out a mixture of liquids based upon their boiling point. Fractional crystallization is separating a mixture based upon their solubilities. So if I had two different ionic compounds dissolved in water, I could start to cool that down. And based upon solubility, one of them would start to precipitate out before the other. I could then filter it to separate out that solid. It's pretty common in chemistry that the adjective fractional is going to describe separating a mixture. Fractional distillation, separating two pure liquids by their boiling point. Fractional crystallization is separating them out based on solubility. Fractional precipitation is separating them out based upon what will react in a precipitation reaction. Chem 1 final project, second semester, where you had your unknown test tube, that was separating out ions based upon how they'd react. So this adjective fractional comes up a lot. Not something, again, that I feel that I'm going to be assessing you on specifically when it comes time to a test. But it's part of that laboratory technique. How can we separate these things out? It deals with intermolecular forces. I think it's a fair thing to be aware of. Okay. Now, liquids would behave somewhat similar to solids. Gases, on the other hand, have an inverse relationship between temperature. Two examples I can give of why gases are actually more soluble at a lower temperature. First one is soda. My daughter asked me the other day about what soda is, so I decided to chemistry her up a little bit. Talked about how it has bubbles in it. It's called carbonation. If it's not a carbonated beverage, it's not soda. So she mentioned to me, well, if I go to Culver's, is there things that I can get that's not soda? I'm like, yeah, there's like pink lemonade. There's fruit punch. If it doesn't have bubbles in it, it's not soda. So then, such a smart kid. She asked me if all the bubbles go away in a 7-Up, is it still a soda? Dang, I guess it's not really a soda at that point because it lost all its carbonation. But if you've ever had a soda that's been sitting out for about an hour or so, it tastes quote-unquote flat. It lost its bubbles. It doesn't taste as good at that point. If instead you opened up a soda and you kept it in a refrigerator and then 2 hours later you took a drink of it, it would lose some bubbles, but it wouldn't lose as many. kind of the analogy I use to explain why gases have this opposite relationship between solubility and temperature is gases are hard to hold onto. Because if you're a gas, either you're probably nonpolar, which means you don't have sites to attract, or you're moving ridiculously fast because you're really heated. Now, we're not drinking ridiculously heated soda, so most gases at normal temperatures are nonpolar. In order to dissolve something that's nonpolar, hard to hold on to, it has to be moving slow in order for the water to surround it. Because if it's already tough to grab hold of, no partial charges or full charges, it better be going slow for us to wrap our arms around it, in a sense. Second example, I think last year I had a couple of fishermen, Will Brzezinski and who else? Colin Steck. Big time fishermen. Ooh, they love this example. In the summertime, so let's stop thinking about how cold it is outside. Let's think about August. And if you want to go fishing, if you set your line for shallow water, you're only going to get small fish for the most part, especially if you go like pan fishing, crappie, perch, stuff like that in a small lake in Wisconsin. Because the deeper you go underwater, the further away it is from the surface that's hot, the water is colder. Colder water can dissolve more dissolved oxygen. And if that's the case, bigger fish that need more dissolved oxygen will be in the deeper water, as opposed to the shallow water. So fishermen can use this application as well of solubility of gases. Remember in Chem 1, yeah, that's all I say there. We had this graph. Again, you guys saw this on the website. I didn't see any issues with questions on that, but the line represents saturation. If you're below the line, you're unsaturated. If you're above the line, it's two options. You have to look at the wording of the question. If it says you're dissolved and you're above the line, then it's supersaturated. But sometimes they'll ask a question of 110 grams of sodium nitrate is, for 110 grams of sodium nitrate is put in water at 20 degrees Celsius, what type of solution is it? If you simply just put a whole bunch of solute in water, it doesn't necessarily mean it's all going to dissolve. Whenever you have stuff that's all dissolved and some sitting at the bottom, it's a saturated solution. Remember in Chem 1, what we had to do was we had to take a saturated solution, then we had to heat it up. We increased the temperature until it all dissolved. It was below the curve. And we cooled it back down. And for some solids, quite frankly, I don't know why some things are better at supersaturating than others. For some solids, that process then will allow all of it to stay dissolved. You dissolve more than you should be able to. Again, in Chem 1, I think we covered saturation pretty well. I simply want to remind you about the solubility curves. Last slide is the only thing that is new, I would say, for today's lecture. Just like last class, when you did the thread and ice activity, you were reminded of the fact that phase change is dependent upon not only temperature and intermolecular forces, topics we covered in Chem 1, but also dependent upon pressure. Solubility of gases is also dependent upon pressure. If you have a greater pressure pushing down on the solution, you can keep more of the gases dissolved inside of it. At about 9 o'clock, if I can last that long, I'm going to be opening up a Mountain Dew can. It's one of the best parts of my day. And what do you notice when you open up a can of soda or open a bottle of soda? You hear type sound. The release of pressure. That pressure is a whole bunch of carbon dioxide that was sitting at the top. When they bottle those sodas or can those sodas, they don't have just regular air or a vacuum at the very top. They put a whole bunch of pressurized gas in there, because now the pressurized gas right above the liquid level is keep making sure that the gases stay dissolved. Because if you have something pushing down on the surface of a liquid, it's preventing the bubbles from coming up. I actually talked about that point when I talked about how the boiling temperature of water is like 70 degrees Celsius in Mount Everest. because at higher altitudes there's less pressure pushing down on the surface, the gases can escape easier. Same thing can be said for soda. I know in Chem 1, and I don't know if I did it with you guys, but when we talk about gases, I bring out the vacuum pump, and it sucks all the air out so there's no pushing down. Some years in Chem 1, if I'm feeling generous, I will use a Mountain Dew for the sake of education. And I'll pour some into a cup, and I'll put it in the vacuum pump. I'll have someone take a drink first, then put it in the vacuum pump. We'll suck out the air. Then they'll take a drink after, and it doesn't taste as good anymore. I mean, it's still better than most things because it's Mountain Dew, but a flat Mountain Dew just isn't that great. Because if there's less pressure pushing on the surface of it, the gases are going to escape a little bit easier. They're not as easily dissolved. So a lot of these last couple of days, I want to remind you to think about not just temperature when we're thinking about how matter behaves, but pressure as well. Now, I have this on the end of the notes. I actually do not care if you know this. This was an equation in our book. I'm not going to attest you on this at all. But this equation is trying to relate Henry's law, how concentration, the molarity of a gas, and pressure, P, is related to one another. Like I said, Henry's law is not something that I plan on assessing you on mathematically. Our textbook, again, old AP standards, has a lot of mathematics that we don't need to be aware of. When I write on the board for homework 20 pages to look through, those 20 pages cover colligative properties inside and out. Anytime you see anything dealing with an equation for the colligative properties, ignore it. You don't need to know it for the purposes of this class. It's just that you used to have to know how to plug those equations in all the time. Which if you do look at those equations, you're going to see molality pop up a lot. Mole fraction is going to pop up. So some of the other units of concentration are used when describing these things. We have a thing of content that we cover this semester. So again, we finished the reading guide dealing with colligative properties, but our textbook did go over a little bit more after just what are those properties. And although there's no direct math that you have to do for colligative properties, even though the textbook has equations all over the place for it, we will have to know a little bit about concentration of ions. So a quick reminder, an electrolyte, like when you drink Gatorade, it's an electrolyte. It's just ions in solution. Again, electrolyte, something that conducts electricity, you have ions floating around solution. So a reminder that NaCl has two different ions floating around in solution. So remember that. We went over drawing of dissolving last class period as well. When I dissolve an ionic compound in water, I'm actually doubling the number of particles that are present in water. It's not just NaCl surrounded by water, it's Na plus surrounded by water. It's Cl minus surrounded by water. The number of particles is what I have to talk to you about today to kind of wrap up colligative properties. Because when, like I have up on the whiteboard, when you add something to water to make a solution, you're adding more things that can be attracted to the water. That affects the behavior of water. Well, the more salt I would dump in that water, the more difficult it would be for it to turn into a gas. Vapor pressure lowering, boiling point elevation as well. Number of particles plays a role in this. A non-electrolyte solution, however, does not dissociate. So I just showed you the video from our online textbook dealing with osmotic pressure for osmosis. And they gave a glucose example. Glucose is a covalent molecule. So it does not break apart into ions when dissolved in water. It's just surrounded by the water. Kind of like our dyes from the lab, we're just surrounded by water. If I were, and here comes molality, to take a 1.0 molal solution of sodium chloride, it would have twice as many particles floating around in it as a 1.0 molal solution of glucose. Because when I put sodium chloride in water, it breaks apart to sodium ion and chloride ion. The one thing, not quite mathematics, but the one thing that you do need to know, and I can all but guarantee it will be on your test, is you're going to have to look at different solutions and determine which one would have the greatest change to, say, the boiling point or the freezing point. And the greater the change from the pure solvent would be based upon how many particles you have. The more stuff that's inside that water, for example, the more it's going to affect how high the temperature can boil at. What's the vapor pressure? What's the freezing point? What's the osmotic pressure? It doesn't matter what type of particle it is. It's all about overcoming attractions or overcoming disorder, if we thought about it in thermodynamic sense. So the water itself doesn't recognize, ooh, that's this type of thing versus that type of thing.
How much does it matter on the size of the particles versus the number of particles?
The size of the particles usually doesn't play too much of a role, but some particles are less soluble in water to begin with, because if you have a big charged product, they can stick together so they're not as soluble. Typically, you're not going to see a problem that's going to play that as a role secondary. It's going to be all based upon what do you have more of. And that's referred to as the Van Hoff factor. Now, in our textbook, it goes over all the calculations. So the Van Hoff factor is the lowercase I. Again, you don't need to know those equations. But here's an example. Sodium chloride would have a Van Hoff factor of 2, because for every 1 sodium chloride, you have 2 particles that come out from it. Calcium chloride would have a Van Hoff factor of 3. Now, Jade's right, calcium is bigger than sodium, but by and large, that does not play a role in this. What's important is the number of particles, not the size of the particles, or even, quite frankly, the charge of the particles doesn't play much of a role. What do you think the Van Hoff factor is for potassium nitrate? Kennedy? 2. It's going to break into potassium ion and nitrate ion. So remember, the NO3 doesn't break apart itself, because that would be breaking covalent bonds. Only the ionic bond will be broken. Let's do one more. What's the Van Hoff factor for sodium sulfate? 3. You'd have 2 sodium ions and 1 sulfate ions. And on my bottom part here, the more particles you have, the greater the change to the freezing point or the boiling point. Again, FP, freezing point, BP, boiling point. So in other words, the greater effect you could lower the freezing point depression, increase the boiling point elevation. If you've ever really looked at road salt, it's not sodium chloride alone. It's a mixture of 4 different things. Some of them are more like a CuCl2, a copper chloride, for example, where there's more particles as well. The more particles, the better off it'll be. Type of questions I would ask you. If you had a solution of the same concentration, and one solution was sodium chloride, and one solution was barium chloride, which one would have a higher boiling point? Sometimes I'll actually give you the molarity on here. Perhaps the barium chloride, because in barium chloride it's BaCl2. There's 3 ions for barium chloride. Sodium chloride, there's only 2 ions. How much sugar or magnesium fluoride? Magnesium fluoride. An ionic compound will break apart into its ions. Sugar is a covalent compound. It won't break apart. It has a Van Hoff factor of 1. The math that you're going to see typically is going to give you a different molarity and then the compound. On that practice sheet you picked up, what you would do is just multiply the molarity times the Van Hoff factor to give you an idea of how many particles are present. Very last thing to note. This Van Hoff factor overall works well. Although at really high concentrations, we start to run low on solvent. So the solvent can't separate all these ions out. Instead, the ions sometimes stick to each other. They pair up, and that actually gives you a smaller I value than expected. When we used to do a lab with freezing point depression, we would notice this, and we would calculate the Van Hoff factor, and then we compare it to what we actually had. And it was supposed to be a Van Hoff factor of 2, and we actually got 1.7. Because at high concentrations, some things start to pair up. But what you should do for the last 10 minutes is look at that practice sheet where I'm giving you concentration and the compound. In order to figure out which one has either a higher boiling point elevation, lower freezing point depression, you would multiply the Van Hoff factor, the number of particles that could break up into, times the concentration. Whichever one gives you a bigger value means you have more particles in that solution. A greater number of particles creates more disorder. It can affect these colligative properties more. All right, so that's what we got the last 10 minutes.